You know instantly that this is a 7. But a computer sees no 7 at all, only a series of pixels, each one a brightness value between 0 and 1. Turning those numbers into the answer 7 is exactly what a neural network does. So let's build one and walk this digit through it. First, unroll the 784 pixel values into input features, and you have the input layer. Each circle is a neuron, and for now, all a neuron does is hold a number, the brightness of 1 pixel. From there, the signal flows through hidden layers in the middle and ends at an output layer of 10 neurons, one for each digit. To see what a neuron actually does, let's zoom in on one. Inside, each neuron is really a small linear regression. Assume this neuron has 3 input neurons with values x1, x2, and x3. Every connection carries a weight. The neuron multiplies each input by its weight, adds everything up, and adds one extra number called the bias. That result passes through an activation function, which decides how strongly the neuron fires and lets the network capture more than straight lines. A favorite is ReLU. It keeps positive signals and silences negative ones. This output then travels down the neuron's own connections, becoming an input for the next layer. But what do weights mean? Assume this neuron has positive weights right where the stroke sits and negative weights just above and below. Bright pixels under positive weights push the sum up. Bright pixels under negative weights pull it down. So this neuron fires only when brightness fills exactly that stroke. This neuron effectively acts as an edge detector, tuned to the top stroke of our 7. In a trained network, early neurons often identify these kinds of simple strokes, while deeper neurons combine them into larger shapes. These are the detectors that light up for our 7, and other neurons specialize in other digits. Now run the whole network. The pixels light up the input layer, every neuron computes its sum and activation, and the signal ripples forward layer by layer. This is forward propagation. The 10 output neurons now hold 10 scores, and the answer is simply the highest one. Here, 7 wins with 94%. Altogether, this network has about 13,000 weights and biases, and everyone was learned from thousands of example digits. So that is a neural network. Pixels become numbers, neurons compute weighted sums with a bias, activations decide how strongly they fire, and stacked layers turn pixels into a prediction. Which leaves the big question: how does the network learn the right weights and biases? We'll cover this in our next video.